see. Okay, cloud recording, check. All right, so it hopped away on me. So the simple explanation of the process here, it was maybe even simplistic, was we're going to find P of X equals K times a bunch of factors. All right, so we identify the roots. So this one has a root. Let me get a different color here. A root of 0. A root of X equals 1. Just write root. X equals 1. And a root of X equals 2. All right. The behavior around this first root looks to be that of a linear equation. All right. Not perfectly linear, but it linearizes itself. All right. It straightens itself out. All right. So that's going to be a multiplicity 1. Now it's a little trickier to tell at least the intent of what this is supposed to be, because you can make a case that it looks linear here also. All right. But in order to get this type of polynomial function, we need power. All right. If I have a degree 4, it might not get it done, because a quartic function, so quartic is degree 4. That's going to have a W or an M look to it. So it's going to look something like that, or like that. And you can kind of see the M or the W in there. All right. That, yeah, maybe. But with this little wiggle in here, it kind of messes everything up. It looks like we got a turn around here. Then we have a little cubic aspect here, and then another turnaround here. This has got, I would say, you can make a case that it's got definitely two recognizable peaks that we call relative extrema. So a relative maximum here and a relative minimum here. But then you also have another maximum over here, and then something going on over here that we have to account for. All right. And like I said, the intent of this problem is for this to be a cubic, even though you might look at it and say, well, it looks like it's a linear, but that's not actually the case. All right. And so a natural question that you might have at this point is, well, how the heck are we supposed to know that on a test? The problem I give you on the test it'll be clear. If there's wiggle going on around the x-axis, in the shape of a cubic, multiplicity 3, it'll be plain and obvious. All right. And then, the last one here, this is definitely a parabolic look to it. All right. So it's got a little quadratic effect there. So multiplicity 2. Right. So what we're looking at here is there's going to be a 6-degree polynomial, right? Because every one of these multiplicities corresponds to a power. All right, so when I say P of X, well, I guess I can go back to black now. P of X is equal to K times a bunch of factors. The factor corresponding with X equals 0, that's just going to be X. The factor corresponding with X equals 1, that's X minus 1 equals 0. So X minus 1 would be the factor there. And X minus 2 equals 0. That'll give you a factor of X minus 2. All right. So again, we'll get the powers involved in a second, but the whole idea is to, unsolve for the root, get 0 alone on the right-hand side of the equation, or either side, doesn't matter, but get 0 all by itself, and whatever's on the other side is going to be your factor. All right. Now, multiplicity 1 gets a power of 1. Multiplicity of 3, power of 3. Multiplicity of 2, power of 2. All right. Now, the assumption here, I mentioned this last time, but the assumption is, well, there's a point on the curve, but there's no reasonable way that you would have been able to pull that from the graph, so I just gave it. And that's what I tend to do in any situation like that. You know, if it's not clear and obvious what the point is, I just tell you a point that's on the curve. All right, so we have an x value here. And this is f of that x value, but I'm going to say p because it's a polynomial function. All right, so we put in negative 120 for p of x. K stays put. We have 3 to the first, 3 minus 1 to the third, and then 3 minus 2 to the second. All right, so cleaning it up, still negative 120 on the left times 3. Then we have 2 raised to the third power, so times 8. And then we have 1 raised to the second power, so times 1. All right. So negative 120 is equal to 24k. Then we're gonna solve for the value of k. Let me get a brush color here. So I'm going to divide that 24 out. All right, and so k alone on the right hand side, divided out on the left, I think that's 5, negative 5. All right, but we could always double check. You know, the numbers won't always be this nice. So, you know, you're probably going to default to using a calculator, but you know, sometimes it is. You know, when it happens, you know, take it and run. So then p of x would be equal to negative 5 x times x minus 1 cubed times x minus 2 squared. And then I would I'd pop that into a calculator, sort of defeating the whole purpose of doing this by hand. But you know, I want to be able to check to make sure that it's going to produce the same graph. All right, so I'll just do it on NumWorks because you know, typing in an equation in a calculator is not really overly specific to different devices. So grapher, go to expressions. Let's see. I guess I could use this template. I don't really need it though. Yeah, I'll just change this one. All right, so we have a negative 5 x, get an x in over there. Then x minus 1 cubed. And then x minus 2 squared. Coincidentally, that just happens to already be in there. All right, so lock that in. Make sure it looks the way you want it to. And, you know, you could go table of values. You could look at the picture. I mean, ultimately, I want these coordinates, as well as this one, to show up in the table. And I want the graph to have this same general shape. It doesn't matter really which order you do it in. All right, so let me go to graph. Yeah, it looks all right. Looks like it's got, actually the one on this calculator looks a lot better than what I put on paper. But it does look like it's going through x equals 0, 1, and 2. It does appear to be linear around x, cubic around 1, even more so than on paper, and quadratic around 2. Now I just want to verify that the appropriate points are there. And really the only one I have yet to verify is the 3, negative 120. So I'll go into the table and I'll take a look. 3 negative 120s in the list. And so there you go. You know, very quickly, again, because it's an emulator, it really isn't the most user-friendly way to go, but let me bring in the TI emulator, that is the Calculator X. And let me bring this up. I'll just swap this one out. Come on. Read my mind, know what I want you to do and do it. All right, so if I put in this equation here, again, you'd hit in the TI, you'd hit y equals, then you type in only the right-hand side, negative 5x, x minus 1, close it up and square it, cube it, then x minus 2, close it up and square it. All right, enter. And then, just you can go to the table second graph and just take a look at the points, right? And the reason I would do it that way, I'm just kind of jumping around. The reason I would do it that way rather than just looking at the picture is because the window aspect of a TI calculator, it's really pinch zoom, and that's so far away from what you would do on an ordinary handheld that it's really not worth looking at least not at the moment, right? But when I look at the values of X that produces 0 for Y, those are the ones that correspond with the roots, and 3 comma negative 120 is a point on the curve. So I'm satisfied that we got the correct equation here. All right. But what we also want to be able to do is sketch a graph from a polynomial function. And when I say sketch, I mean sketch, right? As you move forward and get ready to take calculus, unless, the caveat being, unless this is the last math class you'll ever take, which is possible. That happens for some people. They just need the credits, but they don't have an intention of taking calculus. But if you do intend to take calculus, you don't want to get bogged down drawing graphs, because they're time killers. All right. You want to be able to get a sense of the graph without spending too much time making the graph. All right. So in this regard, it's sort of counter to what you've been doing all these years, like meticulously labeling a graph. Otherwise you lose credit. Oh, I didn't label my axes. Sometimes if somebody asks, okay, what does this graph look like? Sometimes the answer is that, just a quick sketch, right? So we're going to kind of do a hybrid approach, and, we're not going to be as meticulous as maybe in the past, but we are going to try to get the important characteristics of the graph and pull that so that we can actually make a graph in a reasonable way, but also in a graph that'll be informative. All right. So you're given a polynomial function. You want to find the X and Y intercepts. You want to check for symmetry. All right. That's an old concept. And honestly, it doesn't really get much love in college algebra, because you talk about functions, you talk about this symmetry, rules for symmetry, and then you kind of never come back to it again. So until this course, in which case, you have somebody like me to be like, remember when you did that? And you're like, no, I don't. So that can happen, but that's why we review. Right. So we'll check for symmetry, use the multiplicities of the zeros to determine the behavior of the polynomial at the x-intercepts. So this is going backwards. We're going to pull the exponents and use the exponents to help us determine what the graph looks like around the x-axis. Determine the end behavior by having a look at the leading term. Right. That can be tricky, especially since when you look at that first example there, for whatever reason, I have number 2. I guess so. I just broke this up into 3 parts. So I guess it is example 2, but you look at that and you say, well, what's the leading term? You don't have to distribute it out completely, but we should be able to pull the leading term from this. And I'll show you that in a minute. Use the end behavior and the behavior at the intercept to sketch a graph. Ensure that the number of turning points does not exceed 1 less than the degree of the polynomial, and optionally use technology to check the graph. All right. So starting off, we'll just follow the process they suggested, and by they I mean me. Find the X and Y intercepts. So I'll label this based off of what the steps are. X intercept, you replace f of x with 0. All right, because remember, f of x is the same as saying y. If y is equal to 0, then the graph is on the x-axis, making them x-intercepts. All right, so I'm going to take my function, set it equal to 0. 3 is what I wanted to write. Squared x minus 5. It's already in factored form, which is great. So set each factor equal to 0. Well, -2 is a constant multiplier, so we could just toss that. Right? So I would say x plus 3 squared is equal to 0. X minus 5 is equal to 0. I mean, if you wanted to, you could put -2 equals 0, but then you get a contradiction. So you would just cross that out anyway. All right. For the first one, nothing too crazy. Take the square root of both sides. Kind of like step 3 of completing the square, but there's nothing on the right-hand side. So it doesn't really, I mean, square root of 0 is 0. You don't even need a plus or minus. So x plus 3, then solve, you get x equals -3 and x equals 5. Now, you could avoid doing all this work just by thinking about how we came up with the equation from the graph on the previous page. We took the root, flipped the sign, and threw it in a set of parentheses with an x. So why would it be any different the other way? So if you have factor forms, just pull the root out just by negating its sign. And the only tricky instance is when you have a leading coefficient, but you know, worst case scenario, you just resort to solving the equation. All right. Now, for a y-intercept, we replace the x value with 0, so f of 0. All right, we compute that. The result is the y-intercept. All right. So in this case, again, I have f of x equals, I'll just write it again. So I want f of 0. So I'm replacing each x with a 0 and solving. And, you know, sometimes the result is 0, you know, because it is possible that your your y-intercept could be through the origin. But I will tell you that if 0 is not an x-intercept, it's not going to be a y-intercept either. Right? Because if x equals 0 as an x-intercept, that means that the graph is going through, yeah, the x-axis at 0, but that also corresponds to the y-axis at 0. All right. So if it's 1, it's both. If it's not 1, it's neither. All right. So if you get a 0 for x-intercept, then you must also get 1 for y-intercept. If you don't get an x-intercept of 0, you won't get 1 as a y-intercept. All right. So -2 times, those would be 3 squared is 9 times -5. So we're looking at 90 here. So I have an x-intercept of 0, 90. All right. I like to do the math before I go too far down the road of creating the sketch, because I don't want to find out the hard way that I should have scaled my graph after I already started making my graph, most likely in ink. And or at least that's how I am. All right. So we got our x and y intercepts, and we check for symmetry. All right. Checking for symmetry. I mean, we could follow the rules, but I'll explain them. I think that'll probably serve us a little bit better. F of -x is the computation. And so what that's saying is we replace the x in the original function with a -x. If I negate a value, an x value, I'm flipping it over the y-axis. All right. So if I said, for example, I'll do it up here. For example, if I said f of 2 is equal to 5, well, that means I have a coordinate of 2, 5. All right. So if I created a sketch of the graph here, all right, and plotted 2, 5, that would be this point right here. Now, if I figure out f of -2, which is what I would get if I just negated the 2, instead of going 2 units to the right, I'd be going 2 units to the left. If that also happens to be equal to 5, that means I have a mirror image of the first point, f of 2, at f of -2. All right. The distance between this point and the y-axis would then be the same as the distance between this point and the y-axis, making it symmetric over the y-axis. All right. Now, by doing it in general terms, instead of saying f of 2, I say f of x, I'm making a rule that applies for all values of x. So if it checks out to be true, then I know the entire graph is symmetric over the y-axis. Now, if I got, when I put in f of -2, if I got a -5 instead, so let me actually just do that as a separate example, just so I don't confuse the living daylights out of people. Let's say we have f of 1 is equal to 2. Then I compute f of -1, and that gives me a -2. So plot those points, 1, 2, -1, -2, that'd be down here. Now you have symmetry, but that symmetry is not over the y-axis anymore. All right, it's through the origin. All right, so this is my f of -1. This is my f of +1. And again, if it generalizes for all values of x, then I know that I have a graph that's symmetric over the origin. All right, so let's say I have a curve that exists mostly in the third quadrant, or at least the relevant piece is in the third quadrant. Let's say it looks like this, and I tell you that it's symmetric over the origin, then there must be a mirror image going the other way. All right, but then we run into issues of artistic ability or inability as it applies to me. Let's just see. I think I got it. All right, so this is symmetric over the origin, because if I take any point from this part and flip it over the origin, I'll get a corresponding point on the other part of the graph. All right, so this is origin symmetry. We've seen plenty of examples of y-axis symmetry. That's pretty commonplace. The most common one is, I mean, we could go right to the very first function you learned about after you learned about lines back in middle school or early high school, and that would be a parabola y equals x squared. All right, if I tell you that it's symmetric over the y-axis, so y-axis symmetry, there must be a corresponding part of the graph going into the third quadrant, second quadrant, if there's graph in the first quadrant. All right, there is such thing, or a such thing as x-axis symmetry, and we'll get to that later on in the course. We use that for conic sections a lot, like circles, ellipses, and things like that. Right? But those aren't functions, and since the primary focus in this part of the course is discussion related to functions, we tend to skip over that one, at least for the short term. But I did want to take a few minutes to at least give you a little bit of a review of the concept of symmetry. So what I would do then, let me actually bring this over here, just so you can kind of look at it still. So we have our function, I'll rewrite it again. F of x is equal to -2 x plus 3 squared times x minus 5. What I'm going to do is compute f of -x. Function notation could be really tricky to kind of come to grips with, I guess, because there's nothing about this that feels right unless you're really comfortable with the notation. And so what this is saying is it's saying the same thing that it would be saying if I said f of 0. If I said f of 0, I'd replace every x with a 0. If I say f of 2, I replace every x with a 2. If I say f of -x, I replace every x with a -x. So each of these x's, in fact, even this one. So -2 paren, then I'm going to use another set of parentheses to input my -x, and then just build the rest of it around it. All right, and then when we simplify, we get -2, then -x plus 3 squared, then +x I'm sorry, negative x plus 5, kind of treated that like a double negative for no good reason. Negative x minus 5 raised to the first power. All right. Now, I want to simplify this and see, basically see what we come up with as a result. All right, and then we'll use that, we'll just verify it visually. Let me just get better looking equal sign here. But I'll do the part where we verify visually all in one shot after we do all the computations. All right, so in the case of the first set of parentheses, I can factor out a -1. All right, it may not help, it may not do anything. In fact, for both binomials, I could factor out a -1. So I'm going to write this as -2, open a set of parentheses, factor out a -1, which is going to give me an x minus 3, close parentheses twice, incorporate that power of 2. Then for the second one, I'm going to factor out a -1. And the only reason I'm doing that is because I want to have a leading coefficient of 1, just a plain old 1. I don't want to lead my binomial with a negative. I could have written it as 3 minus x instead of negative x plus 3, but it's not going to be as apples to apples when we go to compare to the original function. Okay, so this way is a smidge nicer. All right. So I could pull out a -1 for the second binomial and get x plus 5. All right. So this is the key to everything here. If I take this base, which is raised to a power of 2, I can actually raise each part of that base to the power of 2 separately. So it would be -2. I could say -1 squared, x minus 3 squared, and then I still have that -1 times x plus 5. But that's the least of our worries. The -1 squared, well, any value to an even power is going to go positive. So this is the same as saying -2 times 1 times x minus 3 squared times a -1 times x plus 5. So I can multiply my coefficients here and get a result of 2. X minus 3 squared, x plus 5. All right. And if we compare that to the original function, it looks like it's the exact opposite. All right. But the question is it really? So for that, we could use a test value. And to be honest, you could probably do that. You know, if you want to go point by point, you could plug in like a 5 for x and then plug in a -5, see what happens. Plug in a 3 for x, plug in a -3 and see what happens. Or, I mean, we have the technology. I'm going to go back to the other calculator because just the look of that one really gets to me. All right, so I'm going to go expressions. I'm going to modify. You know, I'm just going to wipe this out and start over. So I'm going to take an f of x. I need, for the original function, it was a -2. Paren x plus 3. Close it up. And that was, okay, just making sure. I had this alarming feeling that it was supposed to be cubed and that I've been doing this whole thing absolutely wrong. But so far, so good. All right, so this is my original function. Then I'm going to pop in another one, which would be the one we just came up with. So 2 paren x minus 3 squared times x plus 5. All right. Now, you could determine symmetry just by, oh boy, sorry. I slid down in the seat. just by looking at the original graph and seeing if it's symmetric. I mean, it's like if you're going to calculator route, you might as well go the distance on that. But these are two equations. And what we want to be able to do is just make a determination of whether these two graphs are exactly the same, in which case it would be an even function. They're not. There's two different graphs that you see there. Or are they exact opposites, right? Now, sometimes it's tricky to tell from a graph, so you go to a table and see what you get for each value of x in terms of a relationship, all right? So if they're exact opposites, then what you put in for 0 or 1 or whatever for one function should lead to the exact opposite value for the other, all right? But like I said before, you could just look at the original function. If you're going to do it by the graph, let's see if I remember how to turn these things off. Yeah, okay. You could look at this graph here and say, does it look like it's symmetric through the origin? So if I find any point on one part of it and flip it through the origin, will I be able to find another part? And, sometimes it's easy to see and sometimes it's not. I think in this case, it's a little easier to see that you're not going to be able to reflect through the origin and get a point that corresponds to the one that you're reflecting. All right, so this one has no symmetry. And that'll happen, when you have transformed functions. If this were 100 units down from where it is, then yeah, you might. Well, actually, I think 90 units because that's what the y-intercept is. But yeah, if that's the case, then you might have origin symmetry. But in its current form, that's not the case. And like I said before, you could go after it using test values. Like if you don't want to manipulate the whole function wholesale, you plug in basically what I did up here. Plug in a 2, plug in a -2, plug in a 1, plug in a -1, and see what you get. Either the numbers will be the same, exact opposite, or different in some other way. That would be y-axis symmetry, origin symmetry, or no symmetry. All right, so for part C, it's use the multiplicities. All right, for that, I could kind of throw it in my solution for A. All right, so the multiplicity of the root, so I guess I'll say part C here. This is going to be a multiplicity of 2, and this will be a multiplicity of 1. All right, and again, that's because we have a power of 2 associated with this factor. I'll tuck in a little teensy tiny 1 there, an assumed power of 1. So that means the 5 has a multiplicity of 1. All right. And the follow-up to that, to determine the polynomial, the behavior of the polynomial at the x-intercept. That's great. We could also use it to determine the behavior of the polynomial overall. All right. Because this has to be a degree 3 polynomial. All right, and you could get that by multiplying your multiplicities. I just wanted to say that, I guess. Adding your multiplicities, all right? Because we have a power of 2 associated with the first factor, a power of 1 associated with the second one. So that comes together to give us a total power of 3, which leads to the degree of the function, all right? Now it's just a question of direction. The leading coefficient here, LC for leading coefficient, is negative, specifically a -2. All right. So for a degree 3 polynomial, it's either going to look like this, some variation of that. That would be for a positive. LC is greater than 0. Or it would go the other way. That would be the leading coefficient is less than 0. And that's just knowing the parent function. Now, to be completely transparent, if I were given a problem that asked me to sketch the graph without any kind of instruction, I'm going to be like, put it in the calculator or make a table of values and start plotting points. All right, because you look at the work we're doing here, and you're like, this is out of hand. But you got to kind of recognize that I'm doing all the explanation, side work to demonstrate the thinking behind why I'm saying what I'm saying. But a lot of this is quick calculation. Like for part A, when we found the x-intercepts, I'm looking at that and saying x equals -3, x equals 5, multiplicity 2, multiplicity 1. Y-intercept, that might take a sec, but I'd do the computation there. Symmetry, same idea, might just go test points. But you could also determine symmetry when the polynomial is expanded out a little bit easier than when it's in factor form. That's not to say that you want to actually have to distribute this out, but it's, if you got to do the algebra one way or the other, you might consider, taking that route. But I'll explain that a little bit more later. The end behavior, all right, we get that based off of this, and so in E, when I say use the end behavior and the behavior of the intercepts to sketch a graph, yeah, that's true, but also throw in there your knowledge of symmetry and also the location of the intercepts. All right, so if I'm doing my sketch, E, yeah, okay, good. I'm gonna do an X and Y axis. Now, before I mentioned that a sketch is a sketch and we don't want to go too crazy with the labels, it's never a bad idea to put X and Y in there though, right? Because it's not always going to be X and Y. And when you get to higher levels, it's going to be other variables. You might have a third axis, going into 3 dimensions. So, just giving a frame of reference. I mean, we all know where the origin is going to be, but in terms of the other coordinates, I'm sorry, the other axes, it's nice to know. So I know that I have an x-intercept at -3 and +5. I'm going to try not to cheat here because you have the graph right in front of you. It's like, did you get that because of all the work that you did, or did you get it because you just looked at the graph? All right. Now I know that it's multiplicity of 2 around -3. So it's either going to be something like this or something like that, but it's multiplicity of 1 around this one. So it's going to go through it either like that or like that. All right. So I use the fact that it has a leading coefficient that's negative. Get a fresh color here. So it's going to start high and end low. But it has to turn around on itself and on the x-axis. Now, I labeled the x-axis by going 1 tick mark equals 1 unit. All right, but on the y-axis, it's a little bit of a different story because I have a y-intercept of 90. All right, so I'm going to go 30, 60, 90. How do I know it's 30, 60, 90? Because I'm going to write 30, 60, 90. If you change the scale of the graph, for me anyway, and for most people, you don't have to label the one that's the default. If there's no label on it, everybody assumes that you're going by ones. All right. So that's fine. It's just when you're going by something other than 1, you want to get a label on there. All right. So I have my x-intercept, my y-intercept, or my 2 x-intercepts. So I know I have to start high and end low. So I'll just put an arrowhead here and an arrowhead here. And it's got to go through these 3 points in such a way that it behaves like a parabola around here. So it must be this form of a parabola. It's got to go this way, right? In order to start up here and then end up back here while also hitting the x-axis in the interim, there has to be a turnaround there. All right. Now it's polynomial, so it'll never come to a point. It's also possible that I could have turning points. I could have parabolic behaviors that have nothing to do with the multiplicity. right? And that's because at some point it has to turn around. It's got to get from here to here. Now it feels wrong when you draw it. It feels wrong to kind of go that way because you're kind of sort of cutting it short. It feels like it goes through a little bit in order to sweep down and around and get that other point. It's a little forgiving in terms of how you draw this. It doesn't have to be perfect. It just has to have those characteristics. All right, so maybe I took it a little wide. Maybe it's something more like this. Like, who really knows? I mean, we know because we saw the picture already. But if it's a sketch, I just want to know that it's going to go through the x-axis and the y-axis where I say it's going to go through. It's going to behave around the axes the way I say it's going to behave. So it actually looks like what I'm saying is happening. And then it has the end behavior that's appropriate. All right. So if you compare this hideous graph, I almost hit the wrong one. I mean, I kind of did anyway. Come on, get in there. Okay. Yeah. Obviously, the one that's on the screen, the calculator screen is more precise. It looks nicer, but this met the standards of what I was asking you to do. Right? It isn't until calculus where you really start learning about how to find turning points that are not on the axis. Right? So there's no expectation that you would know that the turning point is going to be over here somewhere, at least not yet. There are calculator techniques that'll help you do that, but that's kind of defeating the purpose. All right. Ensure that the number of turning points does not exceed one less than the degree of the polynomial. So I have a turning point here and a turning point somewhere over here. That's two of them. You should always have one less turning point at most than the degree of the polynomial. So if I had a polynomial whose highest power was 7, I would have no more than 6 turning points. There's always at most one less. Doesn't necessarily mean there will be 6, right? Because you could have, let's say, a quartic function, a 4th degree polynomial that looks like this. And you're like, there's only one turning point there. All right? There's ways of figuring that out by hand, but it's not really necessary at this point. And then, G was, create the graph on technology, which we already did. All right. The next one really feels like we're going to beat this concept to death. Except, so our roots are going to be the same. Factors are the same, roots are the same. Y-intercept, probably not. We'll take a look. Symmetry, that's going to be the important ingredient here, or one of them anyway. Multiplicity, we already know how it's going to behave. And then from there, we could figure out the behavior. But our x-intercepts are not going to be any different than what they were before because it's made up of the same ingredients, an x plus 3 and an x minus 5. So my roots, x-intercepts, x equals 3, negative 3, x equals 5. The y-intercept, let me do y-intercept on this side like I did before. It's still f of 0, but you could probably crank that out a little quicker now because if you know that in finding the y-intercept, you're just zeroing out all the x values, negative 2 times 3 cubed times negative 5 squared. And this is where we get into that gray area of like how much calculator use is enough. I mean, we're using the calculator as an aid to help us with calculations, but we want to try to get a good understanding of how the structure of the polynomial equation leads to the graph looking the way it does, right? So yeah, am I going to use a calculator to figure out what negative 2 times, 27 times 25 would be? Yeah, I'm going to do that. Negative 1350. So I'm going to really scale the living daylights out of this graph. Sorry, dry throat. So then for symmetry, just do it the way I did before. Put it over here. I'm going to replace each x with a negative x and see where that gets me. All right. But again, like I mentioned before, you could do it with a test point. Right. So let me do it that way, actually, because I already did it the longer way. The issue with doing it with a test point is that you could end up with coincidental values. So I recommend using a couple of test points so that you can really flesh it out. But I'm going to find f of 1 and f of -1. And let me shift this over because I never give myself enough room. All right, so I'm going to get -2 paren 1 plus 3 cubed paren 1 minus 5 squared. And then just do the same thing again, just with a -1. We're looking for what we call a counterexample. Some sort of computational process that disproves a rule, because usually it's easier to disprove than it is to prove. All right, so we're looking at -2 times, this is 4 to the third power, which is 64, and then -4 to the second, which is 16. And then here, -2, then we have 2 to the third power, which is 8. And -6 to the second power, which is 36. So I just crunched those numbers real quick. Oops. Do it again without the oops, though. All right, so -2048 versus -576. So f of 1 is not equal to f of -1, and it's not opposite. All right, equal is easy, like to identify. If the numbers are the same, it's equal. When I say opposite, I mean it's same absolute value but different signs. So in order for this to have been an opposite situation, then when I got -2048 for the first computation, I should have got a +2048 for the other. So using this numerical approach, I would say that there's no symmetry. Then we get our multiplicity involved. All right, so just kind of right back here, this is part C. We have multiplicity of 3, multiplicity of 2. All right, so this is going to be a 5th degree polynomial. All right, once you get as high as 5th, well, actually beyond 3rd degree, it's kind of a mod approach to things. It's like it starts cycling back on itself and behaving in consistent ways. So a 5th degree polynomial is going to have a similar end behavior to a 3rd degree or a 7th degree or any odd degree polynomial. It's going to start high and low, or start low and high. All right, so odd powers have the same end behavior, same type of end behavior, I should say, as each other. All right. So, and if you think about it, just kind of, again, off on the side here, I'll make a little box. So for a linear, it would be a line, but it would start high and low, or start low and high. The exception in the linear case is that you might have something like, y equals 0. All right. So for really what we call invertible functions, it would be just as you're seeing it there. Then the cubic we talked about, starts high, ends low, starts low, ends high. But then you get 5th degree, 7th, and so on. It's just basically the same idea, except there's a little bit more wiggle along the way. So you start high and low, and maybe you have some movement going on like that. 1, 2, 3, 4. Yeah, so that could be a fifth degree polynomial. And then you could have something like going in an increasing fashion, some turnarounds, something in that neck of the woods. All right. So it's still going to have the same, we call it end behavior. We call it that for a reason. It's the behavior at its ends. In each of these cases, we're starting high, ending low. All right. Or vice versa. So we know what the end behavior is based off of the leading coefficient. Leading coefficient is negative. Let me actually highlight this negative. So this has got to be a starts high, ends low kind of deal. So something like that. All right. Increase the power, increase the potential for wiggle. Right. You might have it wiggling all around. Or it is possible that a fifth degree polynomial can look almost exactly like an equivalent third degree polynomial. Right. So, but in making the graph, we now have to account for some pretty extremely large values because the y-intercept is at negative 1350. So I'm going to go by, I guess, 500s here. All right, so my x, my y, I'm going to go negative 500, negative 1,000, negative 1,500, and we'll estimate where the 1350 is. But on the x-axis, I'm going to do the same thing I did before. I'm just going to count out 3 boxes to the left, 5 to the right, or tick marks, I should say. So 1, 2, 3, got a point here. 1, 2, 3, 4, 5, got a point here. And 1350, well, I know halfway between will be 1250, so it's going to be shaded more towards the negative 1500. All right. And we don't have any symmetry on the x-axis, the y-axis or the origin. So we do have to make some assumptions. Now, one of them is that there's going to be a turning point somewhere in this area. And the reason I say that is because we're starting, turning point somewhere in this area. Possibly. It could be on the other side, but somehow we have to get from here to here to here. All right. Now this graph is going to start high and it's going to end low. It's got to behave like a cubic function around this point here. So when I come through, I got to give it a nice wiggle. So something like that. It's got to behave like a quadratic over here. All right. So when I come through this y-intercept, I don't know if I'm going down further. I don't know if I'm going like this, kind of like another cubic affect, or if I'm just turning around and going directly, right? So what I do is I just kind of make an assumption. Probably could have gone a little wider with my V here. I make an assumption and I just start counting. I start counting turning points, right? So if I have no more than 4 turning points, then I've come up with something that could be the graph. And again, that's the name of the game. It's what it could be. All right. So I have a turning point here and a here. That's 2 turning points. Maybe there was another one. It's possible. If I do something like this, so I have 1, 2, 3, 4 turning points. That could be fine. But again, we're doing this without a calculator, so we don't really know. Oops, I don't want to go too crazy here. So you might make the assumption that it's going to look like this, like I did before, and that's perfectly fine. All right. Because like I said, down the line, we'll start learning about where exactly the turning points are and how to compute those. All right. You have to, well, if you're doing it by hand, and it's not something like an ordinary quadratic, to find a turning point, you need to find a derivative. All right. So that's way, early calculus. All right, but for now, we're just trying to get an idea of what the graph might look like based off of the characteristics of the equation. All right. And so the last step is to verify. So we go into the grapher, have a look. And fortunately, this is similar enough where I could just make a couple of changes. That one. And that one. And it's like, let's see how right or wrong I was. Hit OK. Take a look at the picture. All right, so it went down a little bit further over here before coming up and grabbing that. All right, so this is what it should have been. You know, it did have that little extra cubic look to it, and then it came back up. But it's not like you would lose credit for that. You followed the rules. You came up with something that was actually pretty not too far off. All right. The only difference was this little area here. All right. We called it that, they called it this. And they are right, but it depends on what we're using it for. It might be good enough. All right. So one thing I don't want to have happen is everybody does the process, you know, on a test, you follow the steps the way I'm explaining them, and then at the end you erase everything because the graph said something different. That's not the point of the question. The point is for you to make a prediction of what the polynomial would look like based off the characteristics of the equation. All right. And for predictions, it's okay to be wrong sometimes. Now, flat out wrong, you say it's a 4th degree polynomial and it's a 5th degree. You say it's multiplicity 1 when it's multiplicity 3. Those are errors. That's different. All right. But if you did all the background work correct and you graph based off your background work and it's not precisely the same as the graph, that's fine. Full credit. All right. We're trying to make a point here. Right, because later on when we incorporate knowledge of turning points, then you get that extra ingredient that you can use to kind of clean it up. You could also, if you want, do what I did. You know, do your own graph. This is what I came up with, and this is what the calculator came up with. You know, make a correction that way. I see a question. Hand raised.
Yes, Professor. I just want you to scroll down a little bit because when I was working with the idea of multiplicity, of course, the 3 of 3 is like a cube, and then the 2 is like a parabola, right? But this second problem is not showing that of a parabola. So I'm a little bit thrown off because the example before where we start off with a multiplicity of 2, it has that parabolic, you know, shape. And of course, a 1 is more of like almost a straight line. But when we get to number 3, that multiplicity of 2 is not showing the shape on the graph.
So the multiplicity 2, that would be over here. So it doesn't have to be a perfect parabola. Let me get rid of the red here for a sec. Oops. So the multiplicity of 2, it corresponds with the x value of 5. So that's this location here.
Oh, okay. Yeah.
All right. And just to finish the thought here, we have multiplicity of 3. That's
right
giving.
there. Okay, got it. Thank you.
No problem. All right. So again, whether you want to put the corrected one in there or not, that's up to you. But yeah, again, as long as you do the background work, then you got what you need. All right. I'll make up an example for next class where, because I foolishly did not include an example that had symmetry. Right. So, and also they're both odd functions. So I'd like to get in something. Oh, no, I'm sorry, not odd functions, odd degree functions. So I like to get something that's even in there, high power that's even. Do I do it now? I feel like I do it now. I'm going to do it now. So, because I was just looking at what I planned on teaching next, rational functions, which is different enough from what we're doing that it could kind of ruin the flow. So I'm going to make an example 4. Same rule, sketch graph. This is Y type stuff. This handwriting, it's a work of art. I'm going to go with something that's expanded out, right? So a polynomial function that has been expanded. So we'll have to do a little factoring. Do I want to? I'm debating with myself here. I could just, you know what, I'll do it in factor form, and then I'll expand it out just so you can see. So let's say you have f of x is equal to 2 times x minus 2 squared x plus 2 squared. All right, so that's going to be a 4th degree polynomial because I have 2 factors that are each raised to a power of 2. And so if I follow the process, I get my x-intercepts. And the more you do this, the quicker it goes. So we'll have x equals 2, x equals negative 2. Because again, we're just reversing signs here. The y-intercept, you're just going to plug a 0 in for x. So 2, 0 minus 2 squared, 0 plus 2 squared. All right, so that's going to give us 2 times, it's going to be a 4 and a 4, so 32 would be my y-intercept. Coordinates, I mean, you write it as coordinates, or you just write the 32, knowing that you're going to go up 32 units to plot a point. All right. So for symmetry, I'm going to basically do what I did before. This is the danger of making up an example on the fly. I'm not sure what my intent is. I mean, I know what I plan on getting out of this. Why is it not resizing? Resize. Okay, there we go. I'll do it numerically. I was debating whether I should go back to the calculate algebraic approach, but I'm going to just do it numerically. So I'll put part B down here. So I'll use 1 and -1 like I did before. F of 1, f of -1. So 2 times 1 minus 2 squared times 1 plus 2 squared versus 2 times -1 minus 2 squared, -1 plus 2 squared. So 2 times, we're going to get a -1 squared, which is a +1, and then we're going to get a 3 squared, which is a 9. So final product of 18. Right. Then for the next one, 2 times, we're going to get -3 squared, which is 9, and then +1 squared, which is 1. All right, so in both cases, we're getting 18. Right, so that makes it seem like it's symmetric over the y-axis. Right, so you have 2 choices at this point to confirm the thought. One would be, well, pick another set of points. The other would be to go back and do it with x and -x. Right, you're really fine either way. The likelihood that you coincidentally get equality in your solutions for multiple test values is smaller and smaller the more test values you include. So you can just kind of go that route. Or, like I said, you find f of x, which we already know is 2x minus 2 squared, x plus 2. F of -x would be 2 times -x minus 2 squared, -x plus 2. I missed the power of 2 over here, sorry. And then when you factor out a -1, this becomes 2 times -1 squared, x plus 2 squared, then multiply by -1 squared, times x minus 2 squared. All right, because what I'm doing, I'll just show you the side work here. I know not everybody needs it, but I'll do it anyway. This can be thought of as negative 1 parentheses x plus 2. And this one could be thought of as negative 1 parentheses x minus 2, just factoring out a negative 1. All right, since that's being raised, let me get rid of, I don't know why I highlighted that right there. There's no need for that. But since this is raised to the second power, I would take that negative 1 and raise it to the second power. And then I would take, so that's where this is coming from. And then I would take the x plus 2 and raise it to the second power. That's where all this is coming from. All right. So in doing so, I'm able to zap away those negatives. So it becomes 2 parentheses x plus 2 squared, x minus 2 squared, which is the same as f of x. That's the original function. Just, the two factors got swapped, but multiplication is commutative, so you go in either order. And so we have equality here. So f of x is equal to f of negative x. So that means 3 dots in the form of a triangle. If you didn't know, that means therefore. Therefore, we have y-axis symmetry. All right. Now, so this is an either or. You don't have to do it both ways. You do it a numerical approach. I encourage you. Oh, I just X'd something out that I probably shouldn't have. I encourage you to use multiple test values. So instead of just 1 and negative 1, use 2 and negative 2, maybe 5 and negative, whatever you think. All right. You can do it that way, but if you're confident that it's got y-axis symmetry, then you don't have to do it the algebraic approach. If you're unsure, then I think the longer algebraic approach it's more foolproof as long as you do it right. All right. Part C was stating the multiplicities. So we had multiplicity 2 in both cases. We also addressed the end behavior. So this is a power of 4 polynomial. All right, so this is a 4th degree polynomial. All right, now even degreed polynomials, they all have similar behavior, just like the odd degree polynomials do. All right, so I'll just kind of, like I did before, I'll do it off on the side here. You have a parabola, so degree 2. It's either going to be a downward facing parabola or an upward facing parabola. All right. But the key here is if it starts low, it ends low. It starts and ends the same way. Where the odd degreed polynomials, if it started high, it ended low. If it started low, it ended high. So going off of that, we'd have a degree 4. Call those quartic, but we could also call it degree 4 polynomials. So the purpose of this instruction here is not for you to have a list of names of functions to memorize. It's more so that you get a sense of the trend. All right. So degree 4 is going to have the same end behavior. It's just going to have a little more wiggle along the way. I showed you this one before. That's the case of it looking kind of like an M or kind of looking like a W. But the key here is, again, start low, end low, start high, end high. So degree 6, 8, and so on. Same idea, just more wiggle. Look something like that. Again, start low, end low, start high, end high. Right. And this has to do with the type of leading coefficient. Right. So this whole set here is a leading coefficient that's negative. And this whole set here is a leading coefficient that's positive. Right. gonna make this, at least try to make it look a little nicer. All right. So now that I have a sense of the behavior, I also know the y-intercept, I know the x-intercepts, I can start making the graph. So that's part E. I mean, it really doesn't have to be organized by A, B, C, D, E, whatever, but it's there, so it might as well. All right, X and Y axes. I'm going out -2, +2 on the x-axis. I'm not going to scale that, just plot a point for each of them, knowing that it's got to behave like a parabola at both of those locations. All right, the leading coefficient here is positive. All right, so we'll use green here. That's a leading coefficient that's greater than 0. So it's going to be in this category here. It's going to start high, end high. All right, so I could do my arrows, maybe put one here, put one here. And you don't have to do that. Like, I just do that as a little reminder to myself. All right, but I also want to get up to 32 on the y-axis. So let's go by tens there. So 10, 20, 30. All right, so it's going to start high, end high, and behave like a parabola at these locations. All right, so it seems that the only way that that's going to happen, because again, I got some points over here and some points over here, and I have to go through this point. It feels like it's just going to be something like this. I don't know where it turns around because it's got to go back and grab this point. I don't know where that happens, but I do know that it has y-axis symmetry. Well, so let me rephrase that. Without knowing y-axis symmetry, I don't know where it would happen. But since there is y-axis symmetry, I know that whatever happens on the left side of the graph has to precisely match, or mirror whatever's on the right-hand side of the graph. All right. So when I come in, and this could all be like, I don't want to say wrong, but misrepresentation. Maybe it's a little wider and it comes, well, it wouldn't do that because it would go vertical, but you know, maybe it's a little bit more rounded. I really don't know, but I'll do my best here and then just mirror that on the other side. Again, the polynomials never come to a point, so you don't want to go in and out. That's too pointy. So if you feel like that's the case, you know, kind of short it and lean into the turn. And if you're really worried about the quality of your drawing, you know, just make the line, the curve thicker, and it'll hide any imperfections. You know, something like this. We just don't want it to look too pointy. But it doesn't have to be a work of art, because as you can see, I have an app that actually smooths out my writing and it still looks pretty bad, right? So, but this is what I suspect the graph looks like. Symmetry was a big help there, because once I knew what it looked like on one side, it had to look the same way on the other side. So now I just verify real quick. I already forgot the equation. So it's a +2 to get started. X +2 minus, it doesn't matter, but X -2 raised to the third, that's raised to the second, X +2 raised to the second. All right, so this is my equation. Take a quick look at the picture. That looks pretty close to what I did. Obviously better, but pretty close. And so now I'm pretty comfortable with the nature of this graph. All right, so I'm going to just create another problem. You don't have to do it, but this is where we'll start off next class, just to refresh this concept. So I'll call this number 5 and say sketch f of x is equal to x times x minus 1 squared times x plus 1 to the third. All right. So that's the example that we'll start off next one. Like I said, it's not something that you need to do, but it does, I think, help if you have a little bit of familiarity with the problem before we dive into it. And it's kind of like a pace of understanding sort of thing. And also, just as a reminder, I know I added a couple examples today, but when you see the title of the lesson, you know, the next one is lesson rational functions 3.7. That 3.7 corresponds to the chapter in the OpenStax textbook that covers this, that whatever the concept is. So going back to this one, for polynomials, we're looking at 3.4. All right. It's kind of weird. 3.4 covers all of this stuff. It's like 2 weeks worth of classwork. But yeah, it's where you go if you want to find some extra practice. And if anybody needs recommendations on what particular problems to look at, especially before I, you know, as we get closer to a unit test, I'll put a practice test up and you'll see what that looks like. But for now, maybe you feel like you're flying blind. If you need suggestions, just email me and I'll give you a list of things to do. Let's just put it that way. But again, that's all optional stuff. Right. So I am going to stop the recording